Hello and welcome to Fun Facts Online. In the world of materials, some rules seem absolute. Metals conduct electricity. Insulators don't. A copper wire carries a current. A rubber coating stops it dead in its tracks. This simple binary has been a fundamental tenet of physics, the very foundation upon which we've built the entire modern world of electronics. But down in the strange and often nonsensical realm of quantum mechanics, that clear dividing line is beginning to blur and fade. We're discovering materials that defy this simple classification, leading to a fascinating paradox. Insulators that, under special circumstances, behave just like metals. This isn't just a scientific curiosity. It's a frontier of physics that is forcing a fundamental rewrite of our textbooks and paving the way for revolutionary new technologies. To truly appreciate how bizarre this is, we need to revisit the conventional story of conductors and insulators. The quantum mechanical explanation is built on something called band theory. In a solid material, where atoms are arranged in a neat crystal lattice, the discrete energy levels that electrons can occupy merge together to form continuous bands of allowed energy. Think of them like highways where electrons can travel. Two of these highways are critically important: the valence band and the conduction band. The valence band is the outermost occupied highway. It's typically full of electrons that are busy holding the atoms together in chemical bonds. Above it, separated by a stretch of forbidden territory, is the conduction band. This is a higher energy highway that is usually empty. For a material to conduct electricity, its electrons must be able to move freely and gain energy. This is only possible if they can get onto that empty conduction band highway. The difference between a metal and an insulator boils down to the distance between these two highways. In a metal like copper or silver, the valence band and the conduction band actually overlap. There is no forbidden gap. It's as if the on-ramp to the conduction highway is directly connected to the valence band. Electrons can effortlessly slide into the conduction band and roam freely throughout the material, carrying an electrical current. This is why metals are excellent conductors. In an insulator, like diamond or quartz, there is a vast energy gap, a band gap, separating the full valence band from the empty conduction band. This gap is like a huge, insurmountable canyon. For an electron to jump across it, it would need a massive jolt of energy, far more than is available under normal conditions. As a result, the electrons are effectively locked in the valence band, and the material remains an insulator. Semiconductors, the heroes of our digital age, are the middle ground. They have a band gap, but it's small enough that heat, light, or the strategic introduction of impurities can give a few electrons enough of a boost to cross into the conduction band, allowing for controlled conductivity. For decades, this band theory has been incredibly successful. But as we've explored more exotic materials and pushed them to extreme conditions, we've found phenomena that this simple picture just can't explain. Perhaps the most celebrated example of this quantum paradox is the topological insulator. These materials are a true Jekyll and Hyde of the materials world. In their interior, their bulk, they are bona fide insulators with a substantial band gap. But their surfaces tell a completely different story. Their surfaces behave like highly conductive metals. This bizarre dual personality isn't due to any conventional chemical or physical change on the surface. It is an intrinsic, unchangeable quantum state of the material itself. The origin of this property lies in a powerful quantum effect called spin-orbit interaction. In atoms of heavy elements, the interaction between an electron's intrinsic spin, its tiny magnetic moment, and its orbital motion around the nucleus becomes extremely strong. In a topological insulator, this interaction is so potent that it actually inverts the usual order of the energy bands. The conduction band is effectively pushed below the valence band within the bulk of the material. This band inversion creates a topologically twisted state inside the material. But at the surface, where the topological insulator meets the outside world, usually a vacuum, which is a trivial or non-twisted insulator, this twist must be resolved. Quantum mechanics dictates that the band gap has to close at this boundary to stitch the two different types of materials together. This forces the formation of new, gapless electronic states that live only on the surface. These are the metallic surface states. What makes these states so remarkable is their robustness. They are topologically protected. This means they cannot be removed by local imperfections, impurities, or deformations on the surface. It's like having a knot in a rope. You can move the knot around, but you can't get rid of it without cutting the rope. Similarly, as long as the fundamental symmetries of the material are preserved, these conductive channels must exist. Furthermore, in these surface states, an electron's spin is locked to its momentum. An electron moving right will have its spin pointing up, and an electron moving left will have its spin pointing down, for example. This prevents the primary cause of electrical resistance in normal metals, which is when an electron scatters off an impurity and reverses its direction. Here, to reverse direction, the electron would also have to flip its spin, a process that is highly forbidden. This leads to incredibly efficient, almost dissipationless electron transport, opening up tantalizing possibilities for next-generation electronics and quantum computers. Now, let's look at a different kind of rule breaker, the Mott insulator. According to our trusted band theory, any material with a partially filled electron band must be a metal. The reasoning is simple. If the band isn't full, there are plenty of empty energy states available for electrons to move into, allowing for conduction. Yet, in the 1930s, physicists pointed out that many transition metal oxides, which were known to have partially filled bands, were in fact excellent insulators. This contradiction puzzled scientists for years until Sir Neville Mott proposed a revolutionary explanation that went beyond the simple one-electron picture of band theory. Mott's crucial insight was that band theory neglects a critical factor: the powerful repulsive force between electrons, known as Coulomb repulsion. In certain materials, particularly those with narrow energy bands like transition metal oxides, this electron-electron repulsion is incredibly strong. Imagine a lattice of atoms, each with one electron. According to band theory, these electrons should be able to hop from one atom to its neighbor, creating a current. But in a Mott insulator, the energy cost of an electron hopping to a neighboring site that is already occupied by another electron is prohibitively high due to that intense repulsion. The electrons are effectively jammed, locked onto their individual atomic sites. To avoid paying this massive energy penalty, it's a quantum traffic jam on a galactic scale. This Coulomb blockade prevents the flow of charge, turning a material that band theory screams should be a metal into a strong insulator. The Mott insulator is a classic example of a strongly correlated electron system, where the behavior of any single electron is inextricably linked to the behavior of all the others. Intriguingly, this insulating state is not always permanent. These materials can undergo a Mott transition to a metallic state. If you apply extremely high pressure, you can squeeze the atoms closer together. This increases the ability of electrons to hop between sites. If this hopping energy becomes greater than the repulsion energy, the material abruptly switches from an insulator to a metal. This tunable transition makes Mott insulators promising candidates for novel electronic switches and memory devices. Then we have the even more exotic, almost ghostly concept of an excitonic insulator. This phase of matter was first theorized in the 1960s, but remained purely hypothetical for decades before recent experimental breakthroughs finally brought it into the realm of reality. An excitonic insulator can form in a semimetal or a small band gap semiconductor, a material poised right on the knife edge between being a metal and an insulator. Here, the bottom of the conduction band and the top of the valence band are very close in energy. A tiny nudge is all it takes to kick an electron from the valence band into the conduction band. When this happens, it leaves behind a positively charged hole in the valence band. Now you have a negatively charged electron and a positively charged hole, and opposites attract. They can form a bound pair called an exciton. An exciton is a quasi-particle. a collective excitation that behaves like a single particle. In most semiconductors, excitons are created by light and are fleeting, quickly recombining. However, in these finely tuned systems, it can become energetically favorable for these electron-hole pairs to spontaneously form and condense into a new, stable ground state. This condensate of excitons is the excitonic insulator. Because each exciton is charge neutral, the positive charge of the hole cancels the negative charge of the electron. The condensate cannot carry a net electrical current. The formation of these bound pairs effectively opens up a new kind of many-body energy gap, preventing the flow of individual charge carriers and rendering the material an insulator. It's a macroscopic quantum state, similar in some ways to a superconductor, which is a condensate of electron pairs. This field is exploding, providing scientists with a new platform to study exotic quantum phases and explore their potential for creating novel states of matter, such as excitonic superfluids. The quantum paradox manifests in other ways too. The phenomenon of quantum tunneling provides a more direct way for an insulator to show metallic behavior. According to classical physics, an electron encountering an insulating barrier that it lacks the energy to overcome would simply be reflected. It's like a ball that's not thrown high enough to get over a wall. But quantum mechanics reveals the electron's wave-like nature. Its position is described by a wave function, and this wave does not abruptly drop to zero at the barrier. Instead, it decays exponentially through it. If the barrier is thin enough, on the order of a few nanometers, there is a non-zero probability that the electron can simply appear on the other side, effectively tunneling through a classically forbidden region. This allows a small current to flow through a very thin insulator. It's what makes our flash memory work and allows the scanning tunneling microscope to image individual atoms. It shows us that the insulating state is not an absolute barrier, especially at the nanoscale. The thinner the insulator, the more leaky and metal-like it becomes. A more forceful approach is pressure-induced metallization. Subjecting materials like manganese oxide to immense pressures, hundreds of thousands of times greater than atmospheric pressure, can literally squeeze an insulator into a metal. The high pressure forces the atoms in the crystal lattice much closer together. This compression increases the spatial overlap of the electron wave functions on adjacent atoms. As the wave functions overlap more, the energy bands broaden, and eventually, the once large band gap that defined the insulator shrinks to zero. At this point, the electrons are no longer localized and are free to move throughout the material, which now behaves as a metal. But perhaps the most baffling and recent addition to this quantum enigma is the discovery of quantum oscillations in insulators. For nearly a century, quantum oscillations have been considered a definitive signature of metals, and only metals. These are periodic variations in a material's electrical resistance in response to an applied magnetic field. The phenomenon arises from the quantization of electron orbits in a magnetic field, something that should only be possible if electrons are mobile and form a Fermi surface, as they do in a metal. To find this in an insulator would be like finding fish swimming in a block of dry concrete. Yet, in recent years, physicists studying an insulator called ytterbium dodecaboride under extremely high magnetic fields were stunned to observe these same clear, periodic oscillations in its resistance. The material was an insulator by all other measures, yet it was exhibiting the classic fingerprint of a metal. This has led to bold new ideas, including the possibility that the phenomenon is caused not by electrons, but by exotic, charge-neutral quasi-particles that can still form orbits in a magnetic field. As Princeton physicist San-Feng Wu noted, if our interpretations are correct, we're seeing a fundamentally new form of quantum matter. We are now imagining a wholly new quantum world, hidden in insulators. This discovery opens a new chapter in physics, suggesting that our neat categorization of materials is a vast oversimplification. The quantum enigma of insulators acting like metals is a powerful testament to the richness and unpredictability of the quantum world. From the topologically protected superhighways on the surface of special insulators to the quantum traffic jams that create Mott insulators, to the ghostly condensate of excitons and the inexplicable quantum beats found deep inside bulk insulators. These phenomena are forcing a fundamental rethinking of the electronic properties of matter. The clear line once drawn between metal and insulator is fading, replaced by a quantum continuum of strange and wonderful possibilities. This journey into the quantum paradox is far from over. Each discovery not only solves one puzzle, but often unveils deeper mysteries. But the exploration of these enigmatic materials is pushing the boundaries of our knowledge and could unlock transformative technologies. Imagine computers that use dissipationless currents, tiny switches that can be flipped by a change in pressure, or entirely new forms of quantum information processing. The ongoing quest to understand this enigma promises to be one of the most exciting endeavors in modern science, revealing that even in the most insulating of materials, a metallic heart may be waiting to be discovered.